Welcome to a lecture series on hydrogeology. So in this lecture, we are now going to discuss about the groundwater exploration. We have already discussed groundwater exploration, the lithological control, how lithology is helpful for assessing the groundwater. And now we would like to discuss about the structural control. So the structures are so important one, which always control the movement of water or conduits. The movement, it means if the structures like fault, the structures like unconformity, the structures like dike also will play a major role in the movement of water. So we need to know how structure is being controlled. We have different rock types, and different rock types have different structures, and we will see one by one how the structure is controlling. So there are two figures shown here. This is called a crack. Crack leads from the top to bottom, and this is the groundwater, and you have number of cracks in the rock, through which the water will move from the surface and then touches the water table. If you don't have crack here in the top brown portions, then there will not be possibility for the movement of water. And the other figure, once the atmospheric water comes from the atmosphere as a rain, so it falls and it touches on the surface, it started moving as a river, and infiltration starts slowly wherever the crack or wherever the joint or wherever the fault, the porosity and permeability controls the movement of water in different rocks, and slowly it moves on the surface from the surface water body as well as when it travel through the river and then percolate by the pore spaces and permeable interconnected pore spaces and touches the aquifer. This is the water table. So in between, when it moves infiltration, the root of the plant also takes some water for its growth. So that is one. So this is unsaturated zone, this is water table, this is groundwater zone. Your groundwater is there in the soft rock, and your groundwater is there in your hard rock, fractured rock of aquifer. Water stored in underground, through cracks and pores, and you'll be able to get your groundwater below the surface. So structurally controlled. What are the different geological structures are present, such as fold, fault, unconformity, lineament, fractures. So these are the major structures which controls the open spaces or the interconnected open spaces. Sometimes fractures may be within during the formation, but mostly it is in the secondary form. After the formation, you'll be able to get your fractures. So you can see the visual photos, taken excellent photos. There is a break in the rock through which the water will go. It is known factor. After looking the photo, we'll be able to understand that how the water is conduit or moving below the ground. So all these structures have the ability to restrict, or all these structures will have allow the flow of groundwater through the subsurface through them to reach the groundwater. In hard rock terrain or basement rocks, groundwater is mainly confined to the structures such as fractures, fault and lineament, and joints. Places where there is intersection of fractures, intersection of fault, intersection of shear zones are considered one of the highest favorable areas for hosting the groundwater. Developing an understanding of the structural features and their control in groundwater is very, very essential, and then it leads for us to take the water highly economic. The structures like fracture and fault, the structures like subsurface barrier, the structures like colluvial deposits, the structures like weathered zone and vesicular lava, and unconformity and folded structures are the different structures. We will see one by one. The fractured and faulted zone. This is the fracture. You can see the visual photograph. This is the fracture through which the water will move down to the surface. And this is the limestone, caverns limestone. In the caverns limestone, the water is slowly moving down. And this is the fault plane. You can, the movement of water in the cracks. Cracks leads fracture, fracture leads fault. So this wall has gone down, and this wall is the wall which is coming up. So it is a foot wall. It is this hanging wall. The formations are dip down here, and then this is the weaker plates. A fracture is a break, as we know as a geologist. A fault is a break along with the movement, is called as a fault. So this is highly favorable area. A fractured aquifers has limited storage capacity and transport during the movement when it travels in the fractured rock. Fractures are the main and only way the groundwater which is stored, transmitted, especially in hard rock terrain. Without fracture, we cannot expect the groundwater. How much water a well produces depends on the size and shape of the fracture, fracture spacing, interconnection of fractures, and the recharge. You need to have your water. So it depends size of the fracture. If sizes are more, if the depth of the fracture extend up to a longer distance beneath the surface, spacing of the fracture, interconnection of the fractures, and the media, the amount of rainfall in that particular area. If the size is less, it is unfavorable. If the size of the fracture is more, it is good. So both together, up to what depth the fracture extent also plays a major role. And similarly, the spacing between the fracture, if it is less, again the expectation is less with respect to water, and then if it is very closely connected, then it is highly favorable. Although interconnection between the fracture is one, interconnection if it is less, again unfavorable. Interconnection is more, it means all the white spaces or the open spaces should be connected each other so that it will give the way for the movement of water in the subsurface. Storage and permeability depends upon secondary porosity. Fractures of the rock increases their permeability, commonly 100 to 1,000 times depending on the degree of fracturing and depth of the rocks plays a major role. Highly fractured shallow zones are therefore favorable for groundwater. So these are some of the interesting photographs which you can see the cracks, which you can see the fractures, small fractures. This is cracks, and this is small fractures. This is big fractures, and all the fractures are connected. What will happen if the water falls on the surface of this one? Automatically it will go. A lot of spaces over here. You can find the interconnected size is so small, but interconnection is very spacing of fracture is very high, right? It's a bull rock. You see it's being taken out the fractures. The movement also shown that how fast the movement will go, and then this is immobile domain, and this bulk rock fractures and the reliability is very important by looking the real nature of the condition. So direction of groundwater flow through fractures, it's very simply shown here how the direction is here wherever automatically this will go towards to, because of the gravity it will go down wherever the slope is favorable. So this is the direction of groundwater flow. This is aquifer taken from Florida, intermediate aquifer and surface aquifer. Determination of groundwater movement in different formations through fracture system. So there is another very diagrammatic representation how a river system is there. There is a spring here. The water will come down to the river. Automatically, when it is coming, also infiltration starts, and then after falling here, a lot of infiltration. And wherever the least slope is there, it will move, and then wherever the parallel, sometimes the parallel also, you see it's a cold seams are highly favorable for the movement of even subsurface movement of this, this cold seams act as a subsurface movement of river, which moves again parallel to the ground and then reaches the surface, again it is coming down. So why it's spring is coming, because of the pressure on both sides, a confined aquifer. And if the pressure is more in the aquifer, automatically the water will come. So this is not a swell, this is saline water. This is how the movement of water is there. So in granite and fractured aquifer rock, you take what will happen. This is the fractured mantle area, and you just make a bore well and then see, and then this is temporary stream, which is it's a granite boulder. You have a number of cracks, a number of fractures, and interconnected with each other. Slowly, the water will move down through these and then reaches the water table. So this is unsaturated area, this is fractured granite filled with water here, and this is basement, deep basement, fresh basement. So here no possibilities of movement of water. And whereas here, when it comes down and then reaches the basement, depth to basement, after that the water levels will slowly goes up on the top, and then this is the top water level. How a fault zone act, you see the movement of water coming, and then it is filled here, and then the movement is goes here. Look at this very interesting animated movie. After that, it is filled the total area, and then afterwards only it will move down to the this is move, this is foot to foot wall, this is hanging wall. It moves afterwards, right? Faults are one of the most important geological structures control the occurrence of groundwater due to their unique fault zone fabric. Fault can act as a barrier. Sometimes this will act as a barrier. It cannot allow water from one side to another side, but most of the time it doesn't do that, and then it is a good exploration zone. You also can expect a lot of water for the your exploitations. It is highly fractured zone, then secondary porosity will be there. Why it is so important? You will be able to get a lot of joints near to this area. They create surface along with the movement of fluid. Faults are important for groundwater storage and movement. So groundwater in fault zones, you see this is a footwall, this is hanging wall, goes down, and you see this is one formation. Because this has gone down, the formation extend below. This is confined aquifer. What will happen through this water will move from the base, fault zones particularly. You see again here also, this is a well, this is aquifer, this is aquifer is water bearing formation, this is confined one. If you put a bore here, and then you'll be able to get your spring water. And you see the dike. So this is very excellent field photograph. Once if the formation formed, after that, because of the injection of magma, it cross cuts. If it is cut and then settled parallel to the weaker zones, that is called sill. And then if it cut across the formation, this will not allow water. Suppose if percolates the water, this will not allow water from this zone to this zone. If this is strong and this is strong, what will happen? The water will come and then stay here. So if I put a bore here, I will get water, whereas a fellow, if he puts a bore here, he will not get a water. Now this is for a longer distance, I am telling, not for a shorter distance. Assume that if it is a longer distance, more than a kilometer, and if it occurs in the subsurface, it is looking near to the road, we have taken photograph, but if it is down to the surface, deeper in zone, you will not get it. Dike is a sheet of rock that intrude vertically, while silts are the same type of rock that cuts horizontally in another. Dikes are discordant intrusion, so it will not allow water from one part to another part, while silts are concordant parallel intrusion. Dikes and silts may be either magmatic sometimes, or of its sedimentary in origin. Presence of dike and silts in igneous, metamorphic, and sedimentary rocks to form effective subsurface barrier of groundwater flow. The upstream side is suitable for high groundwater potential. The dikes are forming as a natural dam for storing the water. Yes, this at many places, even I've done one work research with respect to this. We have got very excellent result on approaching the dike. The dike will not allow. The dike will not allow water if it comes, and it will act as a storage zone here. So you will put a bore here, and you will get enormous amount of water. And similarly, alluvial deposits. This is alluvium deposit. Whatever the sediments carried by the river in the hilly terrain deposits on the bottom side. It looks like a triangular in shape, and because over the period of time, what will happen? The sand thickness will be more here, and then it will settle down and started to act as a good aquifer. It is good aquifer. This is your, what is that? Good water bearing formations. Alluvial in the foothill of the Himalaya or any foothill, the pediment belt is constituted of the deposits. It is a prism shape or a triangle shape or a prism shape, shaped apron of colluvial fluvial deposits of gravel and sand, perennially recharged by mountain streams continuously. The downstream valleys are filled with permeable sediments and it will act as a good aquifer and you will be able to get huge amount of water here. And what is the process? I said it will deposit in the foothill normally. If you know if the rockfall comes and then you will get alluvial fan. This is alluvial fan and this is rockfall in the hilly terrain because of the movement of the physical weathering as well as because of the rain and the forces acting on the top by construction of buildings. And what will happen, this slowly this will come and then it will move on to the subsurface. This is bedrock cliff. So this is a mountain geomorphology, or sometimes if you study landscapes you will be able to understand all this. So how colluvial process starts and then forming as a good aquifer. And finally we'll go to weathered zone and vesicular lava. Weathering, it leads to weaken and breaking of your rocks in the near surface and subsurface. That will lead as a good conduit of water. So because of the continuous rain action, chemical weathering may happen, and sometimes of big extreme temperature also will leads you to get a lot of weathering in that particular area because of the biological activity. So this is the weathered zone. You look at the weathered zone. This weathered zone is completely, that you will be able to get a lot of open spaces, and all the open spaces are connected in the weathered zone. So this will lead you to get a lot of water in the subsurface, right? This is one, and this is topsoil. This is topsoil cover. In the topsoil cover, the movement of water is there, and this is the second zone, weathered layer, and this is partially weathered layer, fissure zones, and this is the underground water system. And there is a fault also will act as a very good, excellent zone for your expected. And you see, this is vesicular structure, and this is vesicular basalt. So this is primary pore spaces, but most of the pore spaces are not connected. It is in connection between this pore spaces. If in the over the period of time, because of the chemical activity, if it is more, we'll be able to get huge amount of water. The permeability of basaltic rock is highly variable. So this is a pillow basalt. Variable depends upon the rate of cooling. Because of slow cooling, it gets deposited. The number and character of interflow zones, so the thickness of flow. Pillow basalts, and I will show the excellent, because of slow cooling, you'll be able to get excellent deposits. That so the pore spaces are more, interconnection is more expected. This is Malwa, Madhya Pradesh. It is huge amount of water can go, and it is very good, excellent aquifer. The unconformity, you see the break in the sequence of the deposit. So you can find this is one deposit, this is another deposit. Unconformity, the region is another geological important and important structure for groundwater occurrence. You can find the difference between these two, and then this is folded rock. Folded rock also will again help us to see that the movement of groundwater more in the unconformity and folded structures. Especially synclinal, this is synclinal fold, and you can find some synclinal fold here, synclinal fold here is more suitable than the anticlinal fold. The presence of fold indicates that the area is weak and disturbed, hence percolation of groundwater is more in the folded regions. So with this, now we will be able to understand how fold is controlling, how fault is controlling, how unconformity is controlling, how fracture system is controlling. The geologist first should know when he takes up any of groundwater exploration studies. So structure is the prime role in controlling the movement of groundwater. With this lecture is come to an end. Thank you very much.